Welcome all. GATE series, example number 5. Taking the acceleration due to gravity to be 10 meter per second square, the separation factor of a cyclone whose diameter is 0.5 meter and the tangential velocity of 20 meter per second near the wall. This type of problem I have already solved in one of the video, but still I will repeat it again. Separation factor is equal to centrifugal force upon gravitational force in the cyclone separator. Centrifugal force is mass into square of the velocity divided by radius of the cyclone, and gravitational force is mass into acceleration. Remember that this u is basically a tangential velocity. I hope you have gone through cyclone details, and if not, please go through it. Mass from the force terms will get cancelled, so the separation factor is equal to u square upon r into g, where u is tangential velocity. So let's see, in the problem statement, tangential velocity given is 20, so 20 square. Diameter of the cyclone given is 0.5 meter, so radius is half of it, 0.25, and value of gravitational force is given as 10. Remember, when it is mentioned, it is easier to take that value. So 20 square is 400 and 25 into 10 is 2.5. And when you do this calculation, roughly if you do it without calculator, it comes out 25 as a 25, 150, so it comes out around 160. You can even cross check it. So the separation factor for this example is 160. If you have any doubt, you can put it in the comment. Second problem is problem number 6, again from mechanical operation, GATE 2010. The critical speed revolutions per unit time of a ball mill of radius capital R, which uses the steel balls of radius small r, and there are 4 options. Now this problem there is straightforward, but before directly talking about solution, let me tell you some background about the ball mill basically. So this ball mill is used to reduce the size of the particle, or to make the particle more granular in nature, grinding. So it uses different size of steel balls of around 1 to 5 inches, and when this mill rotated, there are 2 forces acting on this particle. One is centrifugal force and another is gravity force. To have a better results or good grinding process, the balance between the gravity force and the centrifugal force is very, very important. if the mill rotates, or if the centrifugal force is very high, you can imagine, if you have done this experiment in mechanical operation in second year of undergraduate level, when the mill rotates, if the centrifugal force, if the speed is very high, the ball will rotate around the periphery of the mill. So there won't be any impact. Impact is one of the method to reduce the size or to grind the material. So there won't be any impact between the ball and the particles. To have a better impact, the balance between gravity and the centrifugal force is very important. So when during rotation, the speed should be maintained in such a way that the particle will go, or the ball will go up and it will fall down, and there will be more impact. And that impact will be very good at the critical speed. So these are the four options. As I told you, that this is very straightforward. Of course, when you do the balance, it comes out to be, the answer coming out is 1 by 2 pi square root of g upon radius of the mill minus radius of the ball, g upon r minus r. We'll solve another problem of critical speed. Critical speed of the ball mill of radius r, which contains balls of radius r, is proportional to, you can see this was the question, same question but asked in a different way. So this is quite interesting. So critical speed is, or even sometimes not standard, but the small n subscript c, the critical speed is 1 upon 2 pi g upon capital R minus small r. Capital R is the radius of the mill and small r is the radius of the steel balls, which is used to grind the particles. So this is the equation or the formula to calculate critical speed. Now if you convert this, now 2 pi and g are constant, so 1 upon square root of capital R minus small r, and when you do this, it is simply 1 upon small r minus capital R minus small r raised to 1 by 2, which is 1 upon small capital R minus small r raised to 0.5, and as it is in the denominator, when it goes up it will become minus 0.5. So the correct answer is small capital R minus small r raised to minus 0.5. So you can see this is the correct answer. One more problem, again from mechanical operation. What is the terminal velocity in meter per second calculated from Stokes law for a particle of diameter 0.1 into 10 raised to minus 3 meter? Density is 2800 kg per meter cube, density of particle of course. Settling in a water, of density of water is 1000 and viscosity is 1 centipoise, which is 10 raised to minus 3 kg per meter second or even Pascal second. I have already explained this in one of the video. So terminal settling, now imagine this is in water and the particle is falling down. So when particle fall down, acceleration decreases. Initially of course acceleration was very high, always high. and it decreases when it comes at a certain point. It decreases in a such a way that when acceleration is 0, and you know acceleration is dv by dt, and when acceleration is 0, the velocity is constant, and that constant velocity is called as terminal settling velocity. And to calculate the terminal settling velocity, there are three different regions I use: Stokes region, Newton's region, and transition region. Of course, the drag force and all comes in a picture. Maybe I will discuss this in another problem. Stokes region is the region where the particle Reynolds number is less than 1. So for Stokes region, the formula to calculate terminal settling velocity is g dp square rho p minus rho divided by rho of f upon 18 mu. Let me explain the terms. G is the gravitational force, dp is the diameter of the particle, this. Rho p is the density of the particle, and rho f is the density of the fluid, now here water, upon 18 mu. Mu f is the viscosity of the fluid. So let us substitute the values. G is again, instead of taking 9.81, it is mentioned that you should take value at 10. Diameter of the particle is 0.1 into 10 raised to minus 3. So 0.1 into 10 raised to minus 3. Remember, this is square. Don't forget to take 0.1, or square of the 0.1. Usually people do a mistake in this. Density of the particle is 2800. So write down 2800 minus density of water is 1000 divided by 18 into viscosity of water is 1 centipoise, of course, but to maintain the unit consistency we have to write 10 raised to minus 3. Let us solve this. You can use calculator, but without calculator also you can solve it. 10 raised to minus 3, 10 raised to 1, 10 raised to minus 3 will be cancelled. So 10 into 0.1 square into 10 raised to minus 3, 1 10 raised to minus 3 is cancelled, into 2800 minus 1000, which is 1800 divided by 18. Now 18 is cancelled, so it becomes 100. 100 into 10, 1000, and 10 raised to minus 3, so it gets cancelled. So this also gets cancelled, so 0.1 square. So 0.1 square is 0.01. So 0.101 or 10 raised to minus 2 meter per second is the answer. There are, I guess I didn't mention options, or maybe options were not given, but of course it doesn't matter. The answer is 0.01 meter per second or 10 raised to minus 2 meter per second, one sec. So this is the terminal settling velocity. Another important point, that when you get such type of answers, you should get an idea whether you are correct or not. So you will get an idea whether you are correct or not from this. You can see 10 raised to minus 2 meter, so which is obviously correct because it is flowing through water. Thank you so much for watching this video. Please watch the videos for next or another problems. Thank you.